Hello everyone, my name is Alex McQuinn. I am a senior physics student at Truman State, and today I'm going to be talking to you about the Casimir effect and its potential applications. So what is the Casimir effect? The Casimir effect describes a force between two very closely spaced parallel conducting plates in a vacuum. This is a very small range force, and the effects are usually only present at distances of about a micron. This effect was discovered in 1948 by Hendrix Casimir, and it has sparked a lot of interest in the past years for its potential use in nanotechnology. Now that you know what the Casimir effect is, I want to get into where it came from. So the Casimir effect has its origin in colloidal chemistry. So colloidal solutions or colloids are mixtures of solutions of small particles, and these particles usually range from about 1 to 1,000 nanometers. Um, and these particles are still able to remain evenly distributed through a solution. Examples include paint, mayonnaise, etc. So the viscous properties of these mixtures are due to van der Waals forces, which was discovered in 1930 using quantum mechanics. So you can see here two particles, and these particles in these solutions have two effects. They have an electrostatic effect due to the polarization of the particles, and they also have this van der Waals force. The van der Waals force is a little bit weaker, but it still plays a pretty big role. So Fritz London showed in 1930 that the interaction between particles was given by basically a bunch of constants over the separation of the particles to the sixth power. But it turns out Fritz London was wrong, and not long after his prediction, Overbeek and Verwey disproved his theory experimentally. They didn't show any theory. They basically just said, yes, this guy's wrong. So they determined that you must consider the retardation effects for this to be correct, for his theory to be correct. And basically the retardation effect is just considering the information transfer from one particle to the other. It takes time. And this is basically just due to the speed of information or the speed of light. So basically, in comes Hendrik Casimir. He was a big theoretical guy, and he became very curious. And so him and his partner started studying these forces between atoms, and they showed theoretically that the interaction was actually 1 over r to the 7th, and this was including the retardation effects. And while they were working on this, they also wanted to consider the interaction between a particle and a perfectly conducting parallel plate. And while they were there, they thought we might as well just study the interaction of two perfectly conducting parallel plates. So using a perturbative quantum dynamic method, using a bunch of complex math, they were able to get the results, which you can see here for two perfectly conducting parallel plates. This was after they got their other results. And Casimir was really surprised that his result was so simple after doing all this complex math. And so while thinking about his results, he got in touch with Niels Bohr, who was a pretty famous quantum physicist. And Niels Bohr he mumbled something under his breath about a 0-point energy. So Casimir thought about this, and he wanted to rederive his results using this 0-point energy. And so basically what the 0-point energy is in a vacuum, known classically as being empty. In quantum mechanics, it's actually filled with all these fluctuating EM waves. And using quantum field theory, there's all these virtual photons that pop in and out of existence. And only photons whose wavelength fit a whole number of times between the plates can exist. And so as you bring these plates closer and closer together, less and less of these virtual photons can come into existence between them. And so this makes the vacuum energy between the plates less than the vacuum energy outside the plates. So there's this net attraction, or kind of this pressure on the outside of the plates. So when Casimir rederived his results using this vacuum energy, he got the exact same thing, which you can see here. The force per area is some constants times 1 over the separation of the plates to the 4th, measured in micrometers. And a dyne is just a unit of force. So he got the exact same results by doing this long computation. And then he got the same thing using the 0-point energy, which is a much simpler approach. And after getting this, he also applied the 0-point energy approach to everything he previously studied with the two atoms and with the atom in the parallel plate, and they also got the same results. So this was also observed 10 years later experimentally. The experiment just had very poor accuracy, but it kind of convinced everybody that this did exist and it was actually a thing. But then it kind of lost steam and nobody kind of experimented on it and came up with any new theory because it was very hard to do experimentally because you had to keep these parallel plates, you had to keep them super parallel, and that was a very hard thing to do. So in 1997, there was actually an experiment done using a torsion pendulum, which you can see here on the right side. So by using a sphere, you could get past keeping two plates super parallel, because for a sphere, there's always a parallel point of the sphere that's the closest. And so when you brought this sphere closer to this plate, you could shine a laser on the top of it and you could detect the movement of the sphere and if there was attraction or not. And so you can see it here under a microscope too. And so this experiment was very successful and it got within 5% of the theoretical value. And so then research exploded. And because everyone saw how easily you could detect it with this kind of system. So in Casimir's time, there was also a prediction for a repulsive Casimir force. And this was achieved by separating plates with a dielectric material or solution. And basically you had to have the three elements of different permeabilities. You could have one perfectly conducting plate, a dielectric solution, and a non-perfect parallel conducting plate. And when doing this, you would actually observe a repulsive Casimir effect. So this was demonstrated in 2009 by a professor and a group of his students. And this has also sparked a lot of interest for its use in application. So the main application of the Casimir effect are these microelectromechanical systems. The microelectromechanical systems are made using microfabrication technologies. These are basically super tiny devices that can harness and exploit the Casimir effect. They are used to measure electric signals and interactions with the environment. And by implementing the Casimir effect onto them, they could be able to harness it for use in the biology field, medical field, and basically just all of technology. So some problems we're having with technology is as technology goes, every year we want to make it smaller and smaller and better. And some problems with making everything smaller is we're running into sticking issues. So as you put more parts on a smaller and smaller chip, they get closer and closer together and they start sticking together in parts that you want to be able to move. And this is due to the Casimir effect. So the Casimir effect can be exploited, or the repulsive Casimir effect could be exploited to avoid these sticking issues in the future. So Casimir-enabled sensors could be practical in a room temperature quantum metrology tool. And so quantum metrology is basically just the study of the measurement of super small things. Right now, we have to use these ginormous expensive machines to be able to measure these super small quantities, whether it be in biology, like measuring heart function and brain function, and many other small measurements in any other field. So these MEMS devices will be important for inertial sensors, which can be seen everywhere from smartphones to airbags. And they could also be used for voltage and current measurement, temperature sensing, and even physical movement. So this effect, as this effect gets studied and developed more, which in the past 10 years, there have been over 200,000 scientific papers published studying the Casimir effect and developing it. So we will start to see the use of the Casimir effect in technology more and more, and it'll have a tremendous impact. So here are my citations, and that's all I have about the Casimir effect. Thank you all for coming.